Hi, this is Dr. Bay and here's Bugsy, and today we're going to talk about stereoisomerism and how to assign stereochemistry. Stay tuned!
Organic chemistry,
taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy. Soaring through the sky, triumphantly we fly, give rise to the complexity of mind. Living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
So one of the components of Vicks vapor inhaler is this molecule shown here. It's very commonly seen in many nasal decongestants. But if you look more carefully at this molecule, you'll notice that it has 4 different substituents around the center carbon atom, shown by an asterisk mark. When a tetrahedral sp3 hybridized carbon atom has 4 different substituents around it, it's called a chiral center. Now notice in this molecule that the methyl group is on a dashed bond, meaning it's pointing to the back. And the hydrogen atom is on a wedged bond, meaning it's pointing towards us to the front. Now if we swapped the positions of the methyl and the hydrogen, we get the following molecule. When 2 atoms or groups around a chiral center can be exchanged to form a new stereoisomer, this chiral center can also be called a stereocenter. What you probably didn't know was that the stereoisomer of a nasal decongestant is actually the molecule for methamphetamine. So this truly shows the importance for chirality, because in this case, you could be using a humble over-the-counter medicine for nasal decongestion, but as soon as its chirality is inverted, it's a totally different molecule with completely different purposes. So in order for organic chemists to assign chirality to a molecule, they needed some type of naming system. And this naming system is named after 3 chemists, Cahn, Ingold, and Prelog. Their system involves assigning priorities to each of the 4 groups attached to the chiral center, which we'll get into the rules next. The first goal that we want to accomplish is to assign priorities to each substituent where 1 is the highest and 4 is the lowest. To do this, we're going to look at atomic numbers of the atoms from the periodic table. The higher the atomic number, the higher the priority. So based off of the 4 atoms directly connected to the chiral center, we have a carbon atom in green, a carbon atom in black, a nitrogen atom in red, and a hydrogen atom in blue. Of the 4 atoms, nitrogen has the highest atomic number of 7, so the substituent in red will be assigned priority number 1. Hydrogen has the lowest atomic number of 1, so it will be assigned priority number 4. And that leaves us with the benzyl substituent in green and the methyl substituent in black, both of which have a carbon atom attached to the chiral center. So if priority cannot be assigned based on atomic number, since they're of the same atom, then we're going to look to the next set of atoms, and then priority will be assigned at the first point of difference. So take a look at the purple arrows. We moved each of them to the next set of atoms, but at this point they're still both carbons. So let's move these arrows one more atom away. So at this point, we are now comparing a carbon atom in green versus a hydrogen atom in black. Since carbon has an atomic number of 6 rather than hydrogen's atomic number of 1, we're going to give the carbon atom a higher priority. So let's assign the benzyl substituent in green as priority number 2, which leaves us with the methyl group in black as priority number 3. Great! We completed goal number 1 and assigned priorities to each of these substituents around the chiral center. Nice job! So now let's move on to goal number 2 of assigning the chiral center as either R or S. To do this, we first have to orient the molecule so that the lowest priority group, number 4, is towards the back. In this molecule, the lowest priority group is hydrogen in blue, which is already on a dashed bond, which means we do not have to do any more rotations to this molecule. Next, we're going to read the direction of the first three priority groups. If these three groups read clockwise, then the configuration of the chiral center is R. If they read counterclockwise, then the configuration is S. So in this molecule, groups 1, 2, and 3 are going counterclockwise. This means that this molecule has an S chiral center. So what happens if the chiral center you're trying to assign contains a multiple bond substituent? Some examples would be an alkene, an alkyne, or a carbonyl group, etc. So let's determine the chirality of the following molecule using the same priority rules that we had just discussed. But let's compare the atomic numbers of the 4 direct atoms to the chiral carbon atom. That would be this chlorine atom, a hydrogen atom, and 2 carbon atoms. Chlorine has the highest atomic number of 17, so we're going to give it priority number 1. Hydrogen has the lowest atomic number of 1, so we'll give it priority number 4. But how do we assign priorities to the alkyne and the ethyl group when both atoms connected to the chiral center are carbon atoms? And if we look until there's a point of difference, the atoms for both substituents seem to be the same. So alkynes can be seen as being connected to 3 carbon atoms. So what we'll do is list out what atoms the first atom is connected to. So for the alkyne, we'll list out 3 carbons in a column. And then for the ethyl group, the carbon atom the purple arrow is pointing to is also connected to another carbon to the right, as well as 2 hydrogen atoms. So we'll list those out in a column too. So now we're going to compare the 2 lists until you see a point of difference. Notice that there is a tiebreaker between a carbon atom in the alkyne versus a hydrogen atom in the ethyl group. Since carbon has a higher atomic number than H, the alkyne will have the higher priority than the ethyl group. So with that, we can label the alkyne as priority group number 2 and the ethyl as priority number 3. Since our lowest priority group, the hydrogen atom in blue, is already pointed towards the back, we don't need to rotate our molecule anymore. And lastly, if we look at the direction of the first 3 priority groups, we see that their configuration is going counterclockwise. That means that this chiral center is S. And the last example that we'll talk about today is when priority group number 4 is not to the back. So what do? Well, it's time to rotate the molecule. And before doing that, we'll assign priorities to each of the substituents in the same way. So pause the video and try this out on your own. So hopefully you were able to assign the priorities to each of the substituents. Notice that priority group number 4, the hydrogen in blue, is on a wedged bond, meaning it's coming towards us, which is not the ideal position for group number 4. So we're going to have to rotate our molecule. Step 1 is to draw the skeleton of the stereocenter without any substituents, keeping the bond types in the same spots. Then choose one substituent in plane to keep in the same position. I usually like to pick the larger one to keep in the same spot, but it doesn't matter which you pick. Next, we're going to rotate group number 4 to go to the back, which would be on a dashed bond. And then we're going to move the other 2 substituents accordingly. So notice that in the original molecule, for hydrogen to move to the dashed bond, it had to move counterclockwise. That means you're also going to move the methyl group and the phenyl group also in a counterclockwise fashion. Now we can relabel each substituent now that group number 4 is to the back in order to determine its stereochemistry. So if we look at the direction of the first 3 priority groups, we can see that they're going in a clockwise manner. This means that the molecule has a chiral center of R. So in summary, today you learned about the Cahn-Ingold-Prelog or CIP rules of assigning stereochemistry. Step 1 is to identify the 4 atoms directly attached to the chiral center. Remember that all four substituents have to be different in order for it to be a chiral center. Step 2 is to assign priorities to each of them based on their atomic number. Step 3 is that if two atoms have the same atomic number, you're going to move away until you see a point of difference. Step 4 is to rotate the molecule so that the lowest priority group, number 4, is pointing to the back on a dashed bond. And lastly, step 5 is to look at the direction of the first three priority groups to determine its stereochemistry. If they're going clockwise, you have an R chiral center, and if they're going counterclockwise, then you have an S chiral center.
Organic.